Okay, so we are going to finish this module in just a few minutes because we are going to cover the tail end of the sectional infinite series. We have talked about the meaning of an infinite series, calculating the sum of a geometric series. We did that last time. And we were just looking at a telescoping series. Here was the telescoping series. And in the telescoping series, we were able to show that the internal terms would add to 0. So let's do this with this other one that we started. And we said, well, if we write out these terms, we obviously are not going to get anywhere with these. So we're going to use partial fractions. So we're going to start off with an is 1 over n squared minus 1. And we're going to write that as 1 over
Recording
n plus 1 times n minus 1, which we are then going to write as a over, okay, n plus 1 plus b over n minus 1. Okay, so when we do this, can somebody please tell me the major equation? What's my major equation? We only need to look at this last part. We just need to look at this part right here. So what's the major equation? What are my roots? How do I solve for A and B?
Is it n plus 1, n minus 1?
Okay, so our roots are n is equal to 1 and minus 1. And so, Brian, can you give me the major equation? Do you remember how to do it? Remember, we multiply by the common denominator.
Right. Are we breaking up the n squared minus 1? Is that what we're breaking up?
Well, we already broke it up. We have n plus 1 times n minus 1. So we broke it up. We want to break it up into the sum of two fractional expressions. So my major equation is when I multiply by n plus 1 times n minus 1.
Isn't it 1 equals a to times n minus 1 plus b times n plus 1?
That's right. Okay, so Brian, do you see how we get the major equation?
Yeah, so it's going to be what, a...
So if you let n equal 1, what do you get, Brian?
You just get 0.
Okay, so 1 is equal to a times 0 plus b times 2. So we get b is equal to a half. And then what happens if n is equal to negative 1?
A times negative 2
Okay.
plus 0.
A plus 0. So a is equal to negative a half. Okay. So now I have split this up.
Oh my God.
I agree with you. Whew. Okay, so now that we have that, we have the sum. So now we have 1 over, I'm so discombobulated. Oh. 1 over n plus 1 times n minus 1 is equal to -1/2 over n plus 1 plus +1/2 over n minus 1. Any questions? Okay. So we can write this as the sum n equals 2 to infinity of 1 over n squared minus 1 is now equal to the sum n equals 2 to infinity of -1/2 over n plus 1 plus 1/2 over n minus 1. Now we can write this several different ways. I'm going to factor out the 1/2. And I'm going to leave the sum n equals 2 to infinity. And I'm going to write it as 1 over n minus 1 minus 1 over n plus 1. Okay, any questions? Okay. All righty.
I have one question.
Yes, PJ. Yes.
Why are we starting from n equals 2?
This series, if we put in n equals 1, we have 1 over infinity. So this series starts at n equals 2.
Okay.
And so you're going to see that just now. So just now you're going to see that if we write this series out now, what is, so this right here is our AN. That's our AN. Okay, times the 1/2. The 1/2 is in there as well. Or we don't have to worry about the 1/2. We can multiply that by the end. Okay, so therefore our first nth partial sum is 1/2 times, when we put in n equals 2, we're going to get 1 minus, and then I'm going to get 1/3. N equals 2, so I'm going to get 1 over 1 minus 1 over 3. Good, that's right. Okay. S2 is A1 plus A2. A1 was 1/2 times 1 minus 1/3. And A2 is 1/2 times, I'm putting in n equals 3. So I'm going to get 1/2 minus 1/4. Okay, so that is 1/2 times 1 minus 1/3 plus 1/2 minus 1/4. And honest to goodness, it looks like nothing right now. I can't see where I'm going to get anything. So S3 is A1 plus A2 plus A3. So I already know I'm going to have 1/2. So let's take that out. So I'm going to have the 1 minus 1/3 plus the 1/2 minus the 1/4. Now, what's the next term? Well, that was n equals 1, so n is equal to 3. So I'm going to have, no, n is equal to 4. So I'm going to get 1/3 minus 1/5. Okay, so now I can see something starting to go away. Okay, let's keep going. S4 is going to be 1/2. The first term gives us 1 minus, that's A1. A2 is going to give us 1/2 minus 1/4. A3 is going to give us 1/3 minus 1/5. And A4 is going to give me 1/4 minus 1/6. Okay, now I can see the pattern. I hope you can see it as well. So the 1/3 is going to drop out. The 1/4 is going to drop out. The next term will be 1/5 minus 1/7. So the 1/5 will drop out. And then the term after that will be 1/6 minus 1/8. So the 1/6 is going to drop out. So every term keeps dropping out except for the last term, which is the 1/n+1. So if I go to the nth term, everything is going to cancel out from before except for the 1/n+1. So the n plus first term, so Sn is 1/2. I'm going to have a 1 and a 1/2. They never get to cancel with anything. And then I'm going to get minus 1/n+1, because that's the last term that never gets canceled off. All right, so I get the nth partial sum is 1/2 times 3/2 minus 1/n+1. Okay, all right, so we're at the end. We now get the sum, n equals 2 to infinity of 1/n² minus 1. It's going to be the limit as n approaches infinity of its nth partial sum. But that's the limit as n approaches infinity of 1/2 times 3/2 minus 1/n+1. And as we know, this term goes to 0 because we have n in the denominator. So this sum of this series is actually 3/4. So notice with the geometric series and the telescoping series, we can not only determine if and when the series converges, we can also find its sum. Okay, so that's a big deal. That is a big deal. So for geometric series, telescoping series, if they converge, we can find the sum. Okay, so this is a big deal for geometric and telescoping series because most series we cannot find the sum. We can just determine that they converge or diverge. Okay, any questions about that? Okay, so that concludes this section and this module. Okay, so now we are going to work on the divergence and the integral test. So this is our new section. And the first thing I want to do in this section is just have a quick review of what we did in the last section. Okay, so in this section, we are going to use the divergence test to determine whether a series converges or diverges, use the integral test to determine the convergence of a series, and estimate the value of a series by finding bounds on its remainder term. If we have time, we will do that. Okay, so here's a reminder from what we just did. The geometric series test. It's going to have a certain form. All geometric series look like AR to the n minus 1 if they start at n equals 1. And if they converge, they will sum to A over 1 minus R. And that's only when the absolute value of R is less than 1. Okay, so we learned that last section. And we also learned about the telescoping series last section. That is, we will write it as a partial use partial fractions, and then we will take the limit of the nth partial sum. If we get a number that's not infinity, the series converges, otherwise the series diverges. Okay, so those are the only two tests that we have where you can actually find the sum of a series. Okay, next is the third test. Okay, so the third test is the nth term test of divergence. All right. It basically says, so I'm going to read the first statement, but I want you to remember the second one. If the summation of AN diverge, if the summation of AN converges, there's a word missing here. Whoa, go back, and don't delete that. Okay, so if that summation converges, then it is a known fact that this series must, the nth term has to go to 0. Okay, so if the summation of AN converges, the nth term has to go to 0. So this is the test. If the nth term does not go to 0, then the series must diverge. I repeat, if the nth term does not go to 0, then the series must diverge. All right, so that is the test. Okay, here's our first example. All right, so our first example is the summation n equals 1 to infinity of 2n minus 1 over n plus 1. So here, AN is equal to 2n minus 1 over n plus 1. That is AN. So now I will look at the limit as n approaches infinity of AN, and that gives me the limit as n approaches infinity of 2n minus 1 over n plus 1. And if I let n go to infinity, I get infinity over infinity. So what does that tell me to do? I got infinity over infinity, guys.
Use rule.
All righty, so now I'm going to use L'Hopital's rule. So when I invoke L'Hopital's rule, I get the limit as n approaches infinity. Johnny, question? Okay, so I'm going to take the derivative of the top. That's going to give me a 2. The derivative of the bottom is 1, so I get 2. So when I take the limit as n goes to infinity of an, I get 2, and it is not 0. So therefore, I can now conclude this series diverges. All right, I got n. So the limit was not 0, so the series diverges. Okay, let's look at number 2. Oh, I knew there was a mistake somewhere else. There it is. But I will fix it. This is supposed to be the nth root and not the fourth root, the nth root. Okay. All righty. So here, a sub n is equal to the nth root of 4 raised to the n power times n. Now I can simplify that as 4 to the n times n raised to the 1 over n power. I can simplify that even more. 4 to the n to the 1 over n is just 4. And then I get n to the 1 over n. So now when I do the limit as n approaches infinity of an, that's just the limit as n approaches infinity of 4 times n to the 1 over n. Now this is a special limit. We talked about this one, guys. You remember? This was one of those special limits I said you need to commit to memory. What is the limit as n approaches infinity of the nth root of n?
So 1.
It's 1. Okay, so this goes to 4 times 1, which is 4, which again is not equal to 0. So this series also diverges. Okay, so far we don't have anything concrete. Let's look at number 3. All righty, so when I look at number 3, an is equal to 1 over n cubed. So when I take the limit as n approaches infinity of 1 over n cubed, I just have the n cubed in the denominator, so I get 0. So what can I conclude?
That it converges.
I cannot.
Wait,
So that's the tricky part of this test. This test says I can only tell you when it diverges. I cannot tell you when it converges. Okay, so here I have to write,
wait, so if it equals 0, then that means you can't tell. If it
this
converges.
test is inconclusive. Okay, it is inconclusive. In other words, for the nth term test of divergence, can only tell if a series diverges, no other information. All right. So the nth term test of divergence can only tell if a series diverges. No other information can be given. Okay, so it does not tell you if the series converges. We cannot learn that from this test. The only thing the nth term test of divergence can tell us is it diverges, or the test is inconclusive. Okay. So here's my summary. So here's the summary. If an is equal to a number and the series is not equal to 0, we know the series diverges. If an goes to 0, the test is inconclusive. Use another test. Okay. So we cannot get, I cannot in any way say the series converges from the nth term test of divergence. Okay, any questions about that? Because that is a big deal. All right, I can see, so if an does not go to 0, I know the series diverges. If an goes to 0, I know nothing. Okay. All righty. Here's the next test. Okay, so the next test is the integral test. All right, so I'll give you a moment to copy this down because this is a little meaty. But it basically says we have a sequence of positive terms. We want to be able to use the an to create a function f. And when f is a continuous positive and decreasing function, then the series and the integral both converge or both diverge, but they can't be doing opposite things. Now it says after a particular value n, I'm not asking you to find that value of n, I'm just saying after a certain point, the function is continuous positive and decreasing. So what do I mean if I have the series? So I have summation. So if an happens to be e to the minus 3n, then my f of x will be e to the negative 3x. Okay, so my function is going to be created from whatever I had for an. Any questions about that? That's how it's going to be created.
So the n just becomes x for the function?
The n becomes x.
Okay.
Yeah, the n becomes x for the function. Okay, so here's one. This is a series you must know. It is called the harmonic series. It is a special series. It is the series of summing up the terms 1 over n. So you have a half plus a third, 1 plus a half plus a third plus a fourth plus a fifth. And you keep going and you keep adding to the series. And the question is, if I summed all infinitely many terms, would this series sum to a value or would it diverge to infinity? Okay, so we are going to use the integral test to determine if that series converges. Okay, so there is a relationship between them. Okay, so what is our series? Our series is the sum n equals 1 to infinity of 1 over n. So our f of x is going to be 1 over x dx. And there is a beautiful relationship between these two. The relationship says if the integral converges, then the series converges. If the integral diverges, then the series diverges. Okay, so let's get cracking. So I need to compute the integral from 1 to infinity of 1 over x dx. And I believe we actually already did this one, but I'm gonna go through it again. So this is equal to the limit as t approaches infinity of the integral from 1 to t of 1 over x dx. So what is the integral of 1 over x dx? What do you get when you integrate that?
Natural log of x.
I get the natural log, okay. So I get the natural log, so this is the limit as t approaches infinity, the natural log absolute value of x evaluated from 1 to t. As the limit as t approaches infinity, the natural log of t minus the natural log of 1. Now, the natural log of 1 is 0. I don't have to worry about that. But as t goes to infinity, so does the natural log. So this goes to infinity. So the whole thing goes to infinity. All right, so what do we find out? This series, this integral diverges. Hence, the harmonic series diverges. Okay, any questions? So right about now, we're using everything we've learned. We're using, when we use trig stuff, we're going to be using all of our integration techniques. We're going to be using our log and exponential techniques. We're using our improper integral technique. So all this stuff that we learned is coming out in series. Okay, any questions about that? Okay,
I have a question about what we started with.
yes.
At the top, we made a sub n equal e to the negative 3n.
Okay.
Why did you why is it equal to e to the negative 3n?
The f of x here.
Yes.
Okay. Because I am trying to write f, whatever it looks like. That is, I want it to be a f of x the same way the series expression for an is a function of n. So I'm just going to take everything that was a function of n, move it to a function of x, and then integrate that.
Okay.
Let's look in this next problem, Prentice. I think it might help with this next problem. Here's the next problem. So I have summation n equals 1 to infinity of n e to the negative n squared. Okay, so now I have to create my function f. All right, so my an is n e to the negative n squared. So therefore my f of x is going to be x e to the negative x squared. Okay, Prentice, does that make sense now?
Yes, so we're substituting the x for n,
And
and then we're taking the integral of that.
then we're going to take the integral. So right now I have the sum n equals 1 to infinity of n e to the negative n squared. And it has a personal invested relationship with the integral from 1 to infinity of x e to the negative x squared dx. Now we could have used tons of different formulas, functions, anything. This just happens to be the example that seemed to work really well for this. Okay, so now I have to compute that integral. The integral from 1 to infinity of x e to the negative x squared dx. Okay, so what happens if this integral goes to infinity? Somebody give me some information. What happens if the integral goes to infinity? Nobody?
It diverges, right?
Okay, the integral will diverge, and that will say that the series will diverge, right? Okay. So let's do this integral. The limit as t approaches infinity of the integral from 1 to t of x e to the negative x squared dx. Okay, how do I integrate that? How do I integrate that?
By parts.
Okay, so you know what? You and so many other people also said the same thing. So this is one of the tricky ones. If there was no 2, I would have to do it by parts. But because there is a 2, I can let u equal, I can just do a simple u substitution. So u can be negative x squared and du can be negative 2x dx. Thank you for your suggestion, because that is a very viable way to try to do the problem. It's tough that way though. It's going to be very hard. So we can't really do this problem by integration by parts because your dv, you won't be able to integrate e to the negative x squared, but if it were just e to the negative x, your answer is dead on. Okay, so x dx is negative 1/2 du. If x is equal to 1, u is equal to negative 1. And if x is equal to negative, I'm going too fast. If x is equal to t, u is equal to negative t squared. Okay. So this is the limit as t approaches infinity. I'm going to make a complete substitution here. So somebody help me out with my complete substitution. What goes at the bottom?
T to negative t squared.
Okay, so when x is, so good, this is negative t squared, and this is negative 1. Okay. E to the negative x squared is e to the u, and then x dx is negative 1/2 du. Okay. So this is -1/2, the limit as t approaches infinity. So what happens? How do you integrate e to the u? What is it? The integral of e to the u is
E to the U.
e to the u. Good. Evaluate it from -1 or -1 to -t². Okay, so I get -1/2 times the limit as t approaches infinity. So now I'm going to get, when I get e, I'm going to get e to the -t² minus e to the -1. Okay, so I'm going to rewrite that just to help my brain out just a wee bit and make it easier for me to take my limit. So limit as t approaches infinity. This is 1 over e to the t² minus 1 over e. Now, as t gets big, t² gets huge. As t² gets huge, e to the t² gets ginormous. As e to the t² gets ginormous, 1 over that becomes 0. So this term goes to 0. So therefore, my answer is -1/2. Oh, just 1 over 2e. And I like 1 over 2e. It's a nice finite number. So therefore, the integral converges. Hence, the series converges as well. Okay, so here is one where you can clearly see that the integral test is going to give you a relationship between the series. Here's the relationship between the series and the integral. Whatever the integral does, the series is going to do it right behind it. Okay? Any questions about that? I forgot my -1/2 here. That's bad. Okay. Don't want you looking at the notes confused. All right, any questions? All right, so the next test is the easiest one of them all. Okay, and I told you there are 12. This one's the easiest one. Okay, test number 5 is the p-series test. So it is the summation of 1 over n to the p. Okay, so now in this test, for these examples, can somebody tell me what is p?
Is p the exponent? So like
Is
the
the
first one,
exponent. So in the first one, p is
2,
2, and the second one, p is
1/2,
1/2, and the third one, p is
1.001.
1.001. Okay, that so so finding p is easy. All right, so for this, we are going to use the integral test. So we're going to find we're going to use the integral test to determine when the P series converges. So we're going to use the integral test to determine the P series converges. Diverges. Okay, so we're going to use the integral test to help us figure this out. Okay, so just like before, there is a relationship by the integral test. There is a relationship between these two. Where is mine? Huh. Okay, there's a relationship between these two. All right, so we need to compute the integral on the right to see when the integral on the left converges. So we will compute the integral from 1 to infinity of 1 over x to the p dx. Now that's the limit as t approaches infinity of the integral from 1 to t. And I'm going to write this as x to the negative p dx, because that's a much easier way to integrate this. And so now that I have done that, this is the limit as t approaches infinity Okay, so now when I integrate that, I'm going to add 1 to it and then divide by it. And evaluate it from 1 to t. Okay. So minus p plus 1 is the same as 1 minus p. So this is the limit as t approaches infinity. I'm going to get t to the 1 minus p minus 1 to the 1 minus p. And this thing is still over 1 minus p. Okay. So now here's where we end up at a juncture. T is going to infinity. So now if P is, let's go back one check. And so obviously this doesn't work if P is equal to 1, right? Because we get 1 minus P in the denominator. But what happens if P is equal to 1? Go back to this. What happens if P is equal to 1? What do you get? If P is equal to 1, you get summation of 1 over n. What is that? P is equal to 1. What is that? There it is. So if P equals 1, we get the harmonic series, which we know diverges. Okay, so we already know now that this series is going to diverge for p equal to 1. Okay, because it's the harmonic series. So now let's see what happens if p is greater than 1. So if p is greater than 1, then 1 minus p is negative. So now I have the limit as t approaches infinity of t to the 1 minus p. That thing, well, I have t to a negative number. So I have something going to a negative number. It means it's getting smaller and smaller and smaller. So that limit is 0 if p is bigger than 1. And then I get the limit as t approaches infinity of t to the 1 minus p. And that limit is infinity if p is less than 1. Okay, so this thing will converge, will equal the limit. So the limit as t goes to infinity of 1 over 1 minus p times t to the 1 minus p minus 1. And this thing is going to go to 0 only if p is greater than 1. And if that happens, I just get 1 over p minus 1. Okay, so now we can see the integral converges only if p is greater than 1. Hence, series converges only if p is greater than 1. Otherwise, the series diverges. Okay. Any questions? All right, here we go. This is the easiest test of them all. In A, p is equal to 2, which is greater than 1, so the series converges. In B, p is equal to, y'all said, a half. That's less than 1, so that series diverges. And I know it seemed weird, but it was important to get one on the edge. P is equal to 1.001. It is still greater than 1, so that series converges. Okay, any questions?
So for the P series test, we don't even have to do all the calculations. It's just saying that P is either greater than or less than 1.
Yep, for P series test, you look at it and you say it's either greater than 1 or less than or equal to 1, and that's where you go. That's the P series. Okay, so what have we learned so far? And where are we going? All right, so this is what we've learned so far and where are we going? Okay, so notice we did the geometric series test and the telescoping series test. They're in red. So the geometric series and the telescoping series are the only series for which we can calculate the sum. All right, so on the test, it's going to ask you, one, identify the type of test, identify the series if you can. So if the series has a special name like geometric P series telescoping, you would write that down. Then you're going to be asked to determine whether the series converges or diverges. You're going to have to state what test you use. And then it will say if the series sum, if it's possible to compute the series sum, do so. And so that means if it's a geometric series or a telescoping series, you are supposed to complete the sum. Okay, so these are in red. Okay, the nth term test of divergence. This is the only test that does not tell us whether a series converges. Okay, this test does not tell us if a series converges. Diverges. Not. Only. This is very important. Okay, this is very important that you know. If I'm using the nth term test of convergence, if I get 12, it diverges. If I get 0, I don't know. Use another test. So if the limit as n goes to infinity of an is not equal to 0. No, equals 0 is what I want to say. If it's equals 0, any questions about that? You must use another test. Okay. Next, we've done the integral test and the P-series test. The next two tests coming up are the direct comparison test and the limit comparison test. And all of these tests actually do tell us whether or not the series converges. Okay, so we have a little time, but I don't want to go too far. Like I said, I don't want to be too far ahead of the other class, trying to keep y'all at the same place. So let's do some practice. All right, so on the test, you will be asked to determine what type of series it is and or what kind of test you would use. So I am asking you to take a look at 1, 2, 3, and 4. If you see one that you recognize and you can say, oh, that's a blah, blah test, then let me know. Or if you can see one, you say, I might want to try this test on it, let me know. So that's the kind of information I want you to have. Hello,
Is this on Thursday's test?
on Thursday's test, you will be asked to identify what type of series it is. Yes.
So for number one, would you use the nth term test?
That won't work, but that's a good guess. Why won't you tell me why it won't work? So in number one, what do you have? What's AN in number one? It is 6 divided by 2n minus 1 times 2n plus 1. And what's the limit of that as n goes to infinity?
Six over infinity.
And 6 over infinity is what? You got six pizzas and infinitely many people come to your party. How much pizza are you getting if you share it? You have 6 pizzas and you got to divide it by infinitely many people. How much pizza do you actually get?
I'm starving.
You get none. All right. Thank you, Brian. You're starving. You're not getting any. Okay. So in the first one, the limit is 0. So now what can I conclude from the nth term test of divergence? Please be careful what you say.
Nothing, right?
Nothing. Thank you. Thank you. Absolutely. We can conclude nothing. Okay, so we got to try another test. So we can conclude nothing. Okay, you're right. We can't conclude anything. So although it looks like we could try the nth term test of divergence, it won't work. I give you a hint. It's one of the ones we had to do a lot of work on. What does this look like? What can I, if I didn't have the sum there, what could I do with that? Could I do with just this piece? Without the sum, it won't let me, yeah, that piece.
Do you multiply the both sides by the common denominator?
Okay, you're getting close. So the first one I can use partial fractions on, right? And then make it look like what kind of series?
Telescoping.
Say that again.
Telescoping.
That's right. Okay, so the first one, if I use partial fractions, it'll be a telescoping series. Okay, how about the second one? There's something right away that should tell you what that series is. Hey, guys.
I'm seeing an n term. So is it an nth term? The n to the minus one?
Okay, which one has the n minus
Oh,
one?
geometric. I'm sorry.
Yup,
I'm sorry.
that one's a geometric series. And this one's an easy one, 1 over the square root of 2, and absolute value is less than 1. So the sum of this series is A, which is 1, over 1 minus R, which is 1 minus 1 over the square root of 2. So if I multiply by the square root of 2, I get the square root of 2 over the square root of 2 minus 1. That's what that series will equal when I sum it up. Okay, number 3.
P series?
That's a P series. What's P?
1/4.
Does the series converge?
No.
So this one you can find. Okay, so the first one was a telescoping, the second one is geometric, the third one is a P series. The fourth one is actually a geometric series. It's not written in the right form, but it is. Okay, it is a geometric series. It's missing the first term. But we could use geometric series on this, or we could use the integral test. So you could rewrite it as a geometric series. Or use the integral test. And that would be integral from 1 to infinity of e to the negative 2x dx. And that converges. So that implies the series converges as well. Okay, I have office hours today at 4. No, I don't. I have office hours today at 3. I have office hours tomorrow at 11. And of course, as always, by appointment. And you guys have a test on Thursday. Okay.